Okay, in the last segment, we looked at a divide and conquer paradigm for designing algorithms. The idea of divide and conquer is to take a large input on which you want to figure out an answer and split it in two halves and then figure out the answer in each half and put it together. We're going to see two examples of that here. We saw the triominoes example last time that was a little bit artificial, but today we'll look at, this time we will look at real examples. So the first one is searching for an element in an array. So imagine this, you have an array of n elements and you're looking for an element x. How long would it take you to find the element x in the array if it's there? Well, if you know nothing about the array, all you can do is compare x with each element of the array until you hit equality. And that could take as long as n steps, and there's nothing you can do about that because x could be hidden anywhere in the array, and you have to look through all the elements to determine if it's there. So that's boring. So let's ask ourselves what we could do if the array is sorted. So if all the elements in the array are in sorted order, in ascending order, does it make it easier to look for an element x? Well, you know from personal experience, if you keep your bookshelf sorted and you're looking for a book, then you know where to look exactly. Or if you keep any other records you have sorted, it's much easier to find a particular record you're looking for. So we're going to sort of capture that in an algorithm here using divide and conquer. So if the array is sorted, we know that if the element x is in the array, it's either in the left half of the array or in the right half of the array. Or it's not there at all. But can we tell very quickly that it's definitely not in the left half or definitely not in the right half? Yes. The way we can do that is to compare x to the middle element in the array. As near the middle as possible. If the array is odd, we may have to choose one or the other. So we compare x to this middle element. Let's call it k. And we ask ourselves, is x greater than k? If x is greater than k, because the array is sorted, we know that x cannot be in the left half. If x is less than k, then it cannot be in the right half. And if we assume, if x is equal to k, of course, we are done. We found x, and we can stop right there. So no matter which answer we get, either we can stop right away, or we can eliminate one half of the array. Okay, so in one step, we've eliminated one half of the array. So if you look at the progression of this kind of running time, we can write that as t of n equals t of n over 2 plus 1. So the time it takes to find an element in a sorted array of n elements is just the time it takes to find an element in a sorted array of n over 2 elements plus the one more step to compare with the middle. So if you solve this recurrence, again, by just expanding a few terms, you find that after one step, you've reduced the argument for the t function to n over 2. After two steps, you reduce it to n over 4. After three steps, you reduce it to n over 8, and so on. And you can ask yourself, how many steps does it take before you reduce that argument down to 1? Because what does it mean when the argument is 1? That just means that we're looking for an element x in an array of size 1. And that's easy to do. It just takes one step to see if that element matches. Okay, so the number of steps it takes to have the array down to an array of size 1 is that k such that n divided by 2 to the k equals 1. So how many times do you have to divide n? What power of 2 do you have to divide n by in order to get down to 1? And the answer for that is the log base 2 of n. So the running time of binary search is log base 2 of n. And if you remember from the picture we drew on asymptotic growth rate of functions, we found that log n was one of the best functions. It grew really slowly, even slower than the function n. So this is a very, very fast and efficient algorithm. One more little point I want to make. In computer science, we often, when we use log, we most of the time are using log to the base 2. So if I don't say what base the logarithm is in this course, it'll typically be to the base 2. Okay, that was binary search, and I hope you understand how it fits the divide and conquer paradigm. Now let's look at another example, merge sort. It's a different sorting algorithm that's going to be better than insertion sort that we saw in the last segment. Okay. In order to explain merge sort, I first have to talk about a procedure called merging. It's different from merge sort. These are two different things. I'm going to talk about merging now. Merging is not a divide and conquer algorithm, but it's a piece of a merge sort algorithm which is a divide and conquer algorithm. So what is merging? You know about merging traffic on two lanes on a freeway, or when you merge into a freeway from an entry. So you know what that means intuitively. It's the idea of two streams of traffic coming together. In our case, it's going to be two sorted arrays of numbers being put together. So you want to take two sorted arrays of numbers and make a single array which is sorted of all of those numbers. Okay, that's what the problem of merging is. So imagine that you have two sorted arrays. Here's two examples. Here's an example. The first array has the elements 3, 7, 12, and 18, and the second array has the elements 2, 5, 16, and 21. And you want to create a single array that contains the results of sorting of merging all of these together. How might you do this? Well, one simple idea is to keep a pointer, which is indicated by these arrows here, this arrow and this arrow. Keep a pointer to the leftmost element of both arrays. Compare the elements pointed to, 2 and 3 in this case, and write down the smaller one in the output array. So you put down the 2 in the output array. Because you've already put down the 2, you can eliminate 2 from the array from which it came and move its pointer one step to the right. And it now points at 5. So again, you compare the two elements pointed to and put down the smaller one, which is 3 from the first array. You put down the 3 and you move the pointer one step to the right. You continue in this manner, comparing 5 and 7 and putting down the smaller element and so on, and thereby you've merged the two lists together. So there's pseudocode in the previous slide for how merging is done, but I hope the example makes it clear that merging is a pretty easy and efficient algorithm. Let's actually ask ourselves how efficient it is. So if the first array is of size n and the second array is of size m, notice that every time we compare two elements from the two arrays, we move the pointer of one of the arrays to the right. So we have to go through n plus m elements. The pointers have to move through n plus m elements, and the pointer is always moving at least one step to the right combined. So the total running time of merging is just n plus m steps, or order n plus m. If the two arrays are both of length n, then the running time of merge is order n. Okay. So now let's use this idea of merging two arrays and ask ourselves how merge sort might work. Okay. So how merge sort works is you're given an array of size n, and we want to produce as output a sorted version of this array, all the elements in this array in sorted order. So we will use the divide and conquer paradigm. Basically, the divide step is going to be really simple. We'll just divide the input array into two halves, the left half and the right half. Okay, that takes no time at all. You just draw a line right down the middle of the input array, and you've got the input split into two problems. Once we've split into two problems, as shown in this example, you have this large array, and we've divided it into two arrays of size. You have an array of size 8, which you've divided into two arrays of size 4 each. Now, we continue to divide further and keep on going until we get arrays of single elements, which are already sorted by definition. Any array with one element is sorted. So once we have these sorted arrays, we start merging together two arrays using the merge algorithm that we saw earlier. So we merge the arrays. Let the array 14 and the array 7 merge together, form an array of two elements containing 7 and 14. Similarly for the others. Now we've got sorted arrays of length 2 each, and we merge. So those are these arrays here. These are the sorted arrays of length 2 each. Now we merge further, and we got a sorted array of length 4. And we merge further, and finally we have a sorted array of length 8 that sorts all the original elements. This is illustrated in the pseudocode on the left, which I will let you look at. So let's understand the analysis of merge sort. So the recurrence for merge sort is that the time it takes to sort n elements, T of n, let's ask ourselves how that happens. To sort n elements, we divide the array into two halves, each containing n over 2 elements. We have to recursively sort each half, and that takes t of n over 2 for the left half and t of n over 2 for the right half, making it 2 times t of n over 2. And after we've got the two halves sorted, we still have to merge the results of the two halves, which is the extra order n step. This is for merging. Okay? So that's explained here. And then when we are down to an array of size 1, it's already sorted. There's no work to be done. So t of 1 equal to 0. And so we can analyze this recurrence relation using the telescoping idea, which basically telescoping just means, replace the argument, replace t of n by whatever value, replace t of n by this, and then within that replace t of n over 2 by its recurrence relation and so on. Keep repeating this until we get down to t of 1, which we know what it is. So you will get this t of n is this kind of long equation, and basically the number of steps you need before you get down to 1 is basically log n, as we saw in the binary search analysis. So we have log n terms, each of the form n, basically. So the total time of merge sort is order n log n. So recall that the time for insertion sort was order n squared. Merge sort works in time order n log n. Which is better? Well, it turns out that log n is much better than n, and therefore n log n is much better than n squared. So merge sort is a superior algorithm in terms of its running time on large data sets.